Hello and welcome back to Series and Sequences. First, I want to thank all the nice people that support this channel by liking and subscribing. In today's part 6, I want to explore the infinite sum of a geometric sequence. So first, let's begin with a little exploration. Let's say we have an infinite geometric sequence given by 2, 4, 8, 16, 32, and so on. You can see that the common ratio here is going to be equal to 2. However, when we add up all of the terms in this infinite sequence, the number is unimaginably huge, thus we use an infinity symbol as a substitute, because there is no concrete value for this sum. However, this isn't always the case and definitely not with all geometric sequences. The case that we just looked at right here is called a diverging geometric sequence. It works the same for negative values. Now, let's take a look at another geometric sequence. An infinite sequence given by 1, 1/2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, and so on. Here you can also see the common ratio is equal to 1/2. Here, when we are computing the sum, we are essentially adding smaller and smaller values. Because by the time we add the 10th term, it's going to be 1 divided by 512. If you put this into a calculator, you will get that this is equal to 0.00195. Going down even further, when adding the 20th term, we would get 1 divided by 524,288. Plugging this into a calculator will give you 0.5 zeros and then only 907. Going even further, these values will only get smaller. So with this logic, when adding the 100th or the 200th term, or even more, we're basically adding 0, since these values are so small, they're basically insignificant. And this kind of sequence is called converging. That's because the values in this series essentially converge to 0. However, there is a criteria that a series have to meet in order to be considered a converging one, and that is that its common ratio in absolute value brackets has to be less than 1. Or in other expression, the common ratio should be strictly between -1 and +1. This makes sense because only when multiplying values which are between 1 and -1 do your terms get smaller and smaller. Any common ratio that is outside of this range will only make your numbers infinitely larger. Now, from the previous video, we know that the sum of a finite geometric sequence can be expressed as u1 times 1 minus r raised to the power of n, and all of that is going to be divided by 1 minus r. However, in the case of an infinite converging geometric sequence, we already know that the common ratio is going to be less than 1. Now, since the common ratio is raised to the power of n, it is essentially going to vanish, or in other words, approach 0 as n becomes larger and larger. So now in the sum formula, what we have is u1 times 1 minus 0 divided by 1 minus r, and so 1 minus 0 just vanishes, and what we have left in the numerator is u1. Another change that we do have to make is that the n is going to become infinity, since now we have an infinite geometric sequence. And this right here would be the formula for the infinite sum of a geometric series. Now please remember the criteria for the common ratio must be a strict inequality. If we pick, suppose, -1, then the geometric sequence would be 1 minus 1, 1 minus 1, and so on. Let's continue. This is called oscillating because the sequence does not settle at a number. Only when the terms get smaller and smaller, heading to 0, can the infinite sum make sense. So now let's take a look at a quick example. Let's say we have a geometric series that converges to 8. That simply means that the sum to infinity of the series is equal to 8. Then we're given that the second term in this series is negative 5 over 2. And we're tasked with finding the common ratio. Let's first write it out. The sum to infinity is given by u1 divided by 1 minus r, and that's equal to 8. The second term of a geometric series can be rewritten as u1 times r, and that's equal to negative 5 over 2. Here we have two unknowns, mainly u1 and r, and we have two equations, thus we can solve a system of equations. An easy way to solve this would be using substitution. I multiply 1 minus r from both sides on top and divide by r on the bottom. So now I have an expression for u1 in two different ways, which means I can equate them to each other. Solving this is quite simple. Let's first open the parentheses. We get 8 minus 8r is equal to negative 5 divided by 2r. We can then multiply the entire equation by negative 2r in order to get rid of the fraction. And lastly, I can move everything to the left-hand side. What we get is 16r squared minus 16r minus 5 is equal to 0. And here we have a quadratic function which can be solved using factorization or the quadratic formula. I personally prefer factorization where possible, and I get two answers. R can be equal to negative 1 over 4, or R can be equal to 5 over 4. However, now, the question is which one would be correct? Since we know that this is an infinite geometric series, that means it's converging. If it's converging, that means it should meet the criteria where the absolute value of the common ratio is less than 1. In our answers, only one of the r's meet this criteria, mainly negative 1 over 4. Here, the common ratio is greater than 1, and with this common ratio, we would not have a converging geometric series. Thus, the only correct answer here is negative 1 over 4. So that's enough for today. In the next video, and the last one for this series, I will show you an application of geometric sequences in real life, mainly calculating money. So I hope this excites you, and I hope to see you there. Have a nice day, and bye.